I would like to start my lecture today. Mainly I would like to talk about the Stokes equation, but first, because the situation is the following. Now, so far we consider I formulate the problem. Anyway, omega t and domain Rm. And now I consider the following situation. So the boundary omega t, boundary omega t has two components. Connected components. Gamma t and gamma d. And component means that it's gamma t and gamma d doesn't meet, has no intersection. Moreover, gamma t is suitably smooth hypersurface. Hypersurface means that the N-1 dimensional manifold. And the gamma d is the C2 smooth C2 hypersurface. And maybe situation in my mind is for example, so omega t is this. On the outside of omega t is the moving, but inside gamma d is fixed. So sorry, gamma d is a fixed. Or ocean problem is a gamma d bottom. It's t. This is like ocean. So bottom of the ocean, and then the surface of the water. This kind of problem. Okay. And then we consider the Navier-Stokes equations in here. And rho. Sorry. Now I consider only the incompressible case. Already I said, well, no, I don't remember. So I considered incompressible viscous fluid. Only consider. Moreover, so usually for example, from the equation of mass, we have rho plus div rho b, but viscosity, incompressibility is written in this way, b. This is incompressible. So volume doesn't change. So give b equals 0. But so combining these two, you have the dt rho. So here is the b dot nabla rho. So Professor Saito told me that this case is the inhomogeneous plus the equation of momentum. This is called inhomogeneous incompressible viscous fluid. Homogeneous incompressible viscous fluid. But for me, this is difficult for me to solve. Therefore, I consider the very standard, very classical one. Mainly, I consider rho is a constant, positive constant. Then automatically this supply satisfy. So conservation of mass automatically satisfied when low positive constant. Then for simplicity, we may assume that rho equal 1 unit density. Therefore, the problem I consider in this lecture is the following. So dt d plus d d d minus equation I equal to f equation and the divergence E is 0 E and then the boundary condition T which is including the surface tension case, but anyway, so far for a while I write member H comma T, and then the fixed boundary on the fixed boundary non-slip condition on gamma D. And initial data and omega T equal 0 is omega T. This is our Navier-Stokes equations in compressible case. So this part is come from the conservation of momentum, and also this too is a conservation of momentum. This is artificial, but it is usually non-slip the domain. The fluid is non-slip onto the gamma D part of the boundary. So it's a very natural boundary condition too. Another explanation of this is, for example, velocity field. Velocity field here, 0. At least the normal component is 0. Means that the velocity, fluid does not. Fluid does attach the omega gamma D. So the fluid does not go overflow. Do not overflow, and also there is not there's no empty places. Yeah, it's a fixed boundary. Yeah, so the flow doesn't go out from this boundary. Also, there's no gap of the gamma and the edge of flow. Fluid. So it's a really the structure of fluid. Character of fluid. Fluid is always want to occupy everywhere. Yeah. This is very natural. Okay, so this is our equation. Then first, of course, we have to linearize. Because so far we don't know how to solve this one except for the linearization. So first, okay, so our strategy now, at least 22 years, what we know is that in some sense, if we solve the nonlinear problem, then we consider linearized equation. Then we construct the one solution for this. So this is one of the typical way, and then only in order to solve the nonlinear problem generally, one typical approach is a linearized equation, and then construct the nonlinear solution to the nonlinear problem by iterations, by a successive okay. So the approach, many people's approach is that to consider generated from these equations. And how to drive the linear problem is the following. Because if you remember that we consider the Lagrangian so now x y plus and oh sorry, stop. 大丈夫ですか? Is equal to f. And in here, f is all the nonlinear term and also external forces and so on. So maybe different f here. Omega. And the divergence u g equal to divergence g omega. And then mu du minus pi n equal to another h gamma on solid gamma. And then u gamma d is equal to 0. And the initial condition. Initial condition is the same. So this is a linearized equation for this equation. Because under this transformation, is, from I mean that the gradient x, I already told you that I think also some this is a time dependent coefficient, but it's a small. So the number x is close to this one. And also n gamma t is I think, I hope, but maybe if I do not, I have not yet given you, then maybe n. Later I will give, but anyway, n plus some perturbation term. Therefore, the normal vector to the gamma t and also differentiation number x is the main part is this one, and also n. And here n is unit or vector gamma, and gamma is just the pullback of this. Okay, so sorry, gamma is up to the gamma t by Lagrangian. So, namely, here is omega is a reference body. So reference body is okay, reference domain, sorry, domain. And d omega, the boundary of omega, have two components, gamma d is set, and then sorry, this is empty set. Sorry, phi sub d is now we consider omega t map, and then this map the phi t is fixed. Okay. The first lecture that I introduced this phi sub t. So in order to drive the equations, the situation is there is a Lagrangian domain, sorry, reference body, reference domain, and then so-called the phi sub d Lagrangian map we consider. Then the image of omega under this map is omega sub t. And then this phi sub t, the domain, the map, the gamma to gamma t, but the gamma d is a fixed gamma t. Anyway, and then the pullback, then you get this kind of equation. There is no linear term. I think already I'm driving something. So this is Stokes equation. So first, maybe several 2 or 3 times I would like to talk about Stokes equation. But anyway, it's not so easy to treat all these non-right-hand side. We need a bit complicated procedure to reduce the problem to the simplest one. So first we have to, but anyway, so first, anyway, we need okay, so sorry, first you have to notice that pressure term P has no time evolution. Meaning that, so here is equation. And then, but the equation dt, only evolution part is u. So dtp doesn't exist. Then how to treat P? Then maybe combining this second equation. So I want to, in some sense, finally I want to eliminate this pressure P. And then we here this okay, so also okay. Anyway, I want to eliminate P finally. So the standard way is we introduce a Helmholtz decomposition. For a while, I explained the Helmholtz decomposition. First, we consider the weak Riemann problem. Say ND problem. It's the following: Laplace nabla u nabla phi omega is equal to f nabla phi for any phi 1, 2 is prime 0 omega. Now I explain this space. Here is the notation. F of G omega is the usual inner product. And omega and also there is nabla u nabla phi. And also YQ prime is later. I explain it. I local and then nabla phi gradient phi is belongs to LQ prime. And then zero here means that gamma equals. Okay. This sobre space is okay. LQ or LQ local. So it's a very special spaces. But to solve this equation, it's a very natural. Meaning, okay, so maybe you are not so familiar. If you are not so familiar with the vector representation, then I explain you. So it's really this equation is just 1, 2, 3, by xj equal to j1 to n p5 xj. Here, or f is a vector. This is a weak form of the following Stokes equation. Sorry, Laplace equation. If okay, you consider this one, these equations, the integration by parts, you get this. So n, okay, for example, the u, or okay, formally, meaning that phi equal the vanishes, gamma d vanishes. Then you make the integration by parts, and then you have plus u phi. Okay, so the dxj come to here. Then you have a Laplace operator, and also here is also you have the divergence f. So you get this is a strong form of these equations. And then actually this phi it belongs to h hat 1 q prime 0. 0 means that phi is actually 0 on here. Then now I assume this one, but this is only the assumption. Therefore, in order to get this equation, for example, we have the Neumann condition for du d nu n of direction part is n d f like. Then this integration by parts does hold. Why? Because we have no information phi on gamma d. Therefore, if this hold, then you can get this equation on boundary automatically. Understand what I mean? Yeah? Now, yeah, formally I assume this one, then you get this. But actually, I only consider, I only assume that phi gamma, phi boundary value of phi on gamma is there. That we have no information here. But then still, we have this formula. Then you have this partnership. This equal this on gamma. So this is additional condition for you. But this additional condition is necessary when you consider the strong solution, strong formula. But now only consider this weak formula. Therefore, you don't need these conditions. This is a weak formula of the Laplace equations. So this is important for when you consider the Navier-Stokes equation or Stokes equation. It's a very fundamental, very necessary condition to consider, necessary equations to consider. And then okay, so if we consider the Hilbert space, then this theorem, this representation theorem, we know the unique existence of solution. U H hat 1, 2, namely Q equal 2 case. We know the probability of it. Okay, so this for any F L2 omega n there exists unique U H2 omega of solution of this. Okay. So, because 120 omega is pi L2 log omega plus pi L2, and then this space has a Hilbert structure, every pi. This is inner product of this space. Inner product of this space. And then by using this, so you can say that this space has inner product spaces. Nice cool. Of course, you have to show that the completeness, but maybe it's okay. We assume that we know that the completeness of this space by using with respect to this norm. Then you can apply the least representation theorem in Hilbert's space theory. So you know the existence of unique solution this problem. So L2 is okay, but general LQ is a problem. We don't know the general theory for the LQ. Two LQ. We have general theory. So when you want to consider the Navier-Stokes equation, then first you have to consider this weak Dirichlet-Neumann problem. And then you have to show the existence, unique existence theorem for this weak Dirichlet-Neumann problem, Neumann-Dirichlet problem. For example, the omega is bounded domain. Or half space, of course Rn, or half space, or exterior domain, or tube, layer. At least I know these spaces. In these spaces, you can solve weak Neumann-Dirichlet problem for any Q. So omega is a bounded domain, or Rn, half space Rn plus, or exterior domain, or tube. Tube is like define a tube or layer. This is tube layer. Okay, layer is maybe wide spaces. Two wide half space. Oh, no, sorry, plane. Excuse me. Two plane. So between two planes is layer. So these spaces you can show the unique existence of weak Neumann-Dirichlet problem. But if you want to consider anyway, if you consider the Navier-Stokes equations more general domain, then first you have to show that the existence of weak Neumann-Dirichlet problem. One of the typical approach is, of course, L2, but one of the typical approach is you consider this intersection problem. So then you can solve the weak Neumann-Dirichlet L2. But then you use some kind of regulated theorem of the elliptic problem. So L2 solution also you can say that also LQ. The right member F, for example, right member F belongs to L2. Then your solution B is H hat 1. This is one of the typical argument to solve Navier-Stokes equations in a more general domain. But of course, you need some more assumption or regulate from the band F. So in this lecture, I assume, in this lecture, we assume one of the essential assumptions is that weak Dirichlet uniquely solvable. So, meaning, namely, or any F, LQ, omega N, F is a vector of LQ omega function, N vector of LQ omega function. There exists a unique V U H at 1 Q L omega such that number of 5 omega of any 1 prime. We assume this. And then, of course, you can easily show that this gradient U can be estimated. Closed graph theory. if you use a closed graph theory, then you can show this one. So that this is some constant C, and then all the solution U satisfy this inequality. It's a closed graph theory. This is you can show. Patient. This is a sum. Yeah, this is a closed graph theory. Okay. So far, I always assume that this weak Neumann-Dirichlet problem is uniquely solvable. Even I do not mention this one, always I assume. I consider such domain omega. In some sense, this is an assumption for domain omega. Then Helmholtz decomposition. Sorry, first of all, maybe not. Also, you can solve for any F, LQ, F, Q. There exists a unique U. It's H1Q omega plus H hat 1 0 omega is a summation of solution. You satisfy and U equal F on boundary. In fact, if you put U minus F, B equal U minus F, then number B, number phi, in solution to gent, okay. Yes. E is a function in H hat 1 Q 0, which satisfies this. Then you satisfy this equation. Okay, so we can solve inhomogeneous problem. All right. We assume that the existence of this, this is solution boundary value of U is zero vanishes on gamma. Zero means that the U vanishes on gamma. But then you can consider the non-homogeneous boundary value F on gamma. But how to solve is just you consider V is equal to U minus F. No, sorry, it's okay. V is U minus F. Then V, if U satisfy this equation, excuse me, then V satisfies this equation. And this weak Neumann-Dirichlet problem can be solved by assumption. And then V is here. Therefore, U is F plus B. Okay. All right. Now we consider how to treat. Secondly, how to treat this. Sorry, excuse me, I forgot. Helmholtz Decomposition. Anyway. It's following. So given F, let my U is a solution of this weak problem. Weak Neumann-Dirichlet problem. Sorry. And then set G is equal to F minus number U. Then from this formula, G satisfy any. It's a trivial thing. So phi F is decomposed D plus U. Okay. It's a bit trivial. So we now therefore we introduce a space. So solenoidal space is G is the subspace of LQN, which satisfies U by Y. This is a solenoidal space. So strong form of G. Strong form is just the integration bypass. G equals 0. So usually the solenoidal space means that G is a LQ function, and then the div G vanishes in a distribution sense. This is a solenoidal space definition of the solenoidal space. I think maybe usual books or usual contents, but maybe this is more rigorous. Okay, so solenoidal space is just the LQ function, vector of LQ functions, and then the G number phi is there. Then here is gradient space. So gradient space G Q is a gradient space where U belongs to H. Q. So it's the subspace of LQ. Then Helmholtz decomposition is the following. So LQ omega n is decomposed by solenoidal space plus this gradient space, gradient space. This is so-called Helmholtz decomposition. Okay, of course, we know that the LQ omega is equal to JQ omega. So already I gave you that the any f of this decomposition, and then the plus means that this is direct sum. You have to show that the direct sum, meaning is that G meaning G. Okay, so if you direct sum is G and what to say H belongs to JQ omega intersection EQ, then H equals 0. This shows you that the direct sum. So, but how to prove it? It's easy because it's H belongs to the intersection of these two spaces. Therefore, H belongs to this one. So H can be written in this way. And then also the JQ omega. It's meaning is that number U, number phi, omega is equal to 0. Phi. Then we assume that the unique existence. Therefore, we know that the uniqueness of this solution. So therefore, this is assumption, but anyway. So H equals 0. So unique the assumption of the unique existence of weak Neumann-Dirichlet problem guarantee this decomposition, Helmholtz decomposition. Yeah. This is maybe you know very well, but this Helmholtz. But Helmholtz decomposition is implied by the unique existence assumption of the unique existence of the weak Neumann-Dirichlet problem. So usually, I want to write that the FLQ P, YP, I don't know. P is the solenoidal part, G, and the Q, I is equal to U. Definition. Therefore, F is here. So P just so P is projection from this one, from L to omega L to this solenoidal part. Q is a This is the Helmholtz decomposition. Now, now how to treat? I want to tell you how to treat these conditions. So, if you look at the first equation, dtu minus du E is equal to F. The first equation. Then now for any phi, consider another phi. Okay, this is equal to dtu phi minus du phi plus another p over phi. Now, what I want to do is that I want to drive the equation for pressure P. So, we consider this. Then slightly the formal argument. Right. This is the t time derivative is a parameter. So now, sorry, now I omit omega. Omega is omega, but it is integration only x variables. Therefore, t is the parameter here. So this is 1000 dB outside. And then, okay, formal calculation, but anyway, this is divergence u phi. So divergence u equal divergence g. Okay. So therefore, it's rather formal calculation, but anyway, you get sorry. G. Right. Now I consider the problem from the necessary conditions. Usually, to solve the problem, PDE, first we consider the necessary conditions. And means du is what? It's like the I component is so therefore this is Laplace operator UI. This is divergence U. Okay. So usually you have to remember this is Laplace U and give U. Under this, okay. Yeah. Then D, okay, and then mu du over phi is plus u over phi u du phi. And this is G, small g. And here is also the very formal calculation is minus mu divergence. Formal calculation. Then is equal to minus mu plus g I. And then Laplace g. This is now scalar, so Laplacian is grad g, grad g. This is also formal calculation, but anyway, you get this one. Okay, formal. But this number going to here, then the divergence. And then divergence u equals small g. And then this is scalar, therefore this number going half number is gradient. So this is 2 mu number g number phi. Therefore, you get the equation for number p. So therefore, you have number p, number phi to dBf as okay if minus dpg from number p plus g. Sorry, 2 mu grad g for a. Okay. Therefore, for example, let P1 it's hot. Which is a solution of this one. Then you can reduce the problem in the following. So now you divide pressure term P over Q. I forget. Then you get maybe P. Then you get the equation for the dt u minus du plus nabla mu q, new pressure q is equal to F minus nabla P1 omega And then in this case, we are expected that d equal. Sorry, new b. Now we are solving this b for 0. B is right hand side is this one, and B, I think, other D. So B, new Q, and it's now H. So this is one of the way to then. Sorry, it's okay, but how to recover you? No, sorry. Excuse me. Then you construct. For example, you construct you solve this equation with some boundary conditions. So this is heat equation in some sense. This is because some kind of heat equation. Therefore, then you can say that if you solve this one under some suitable boundary condition, then you can prove that U is equal to T. Maybe later I give you more precise, but now the idea how to solve the equations. So the first, anyway, the Helmholtz decomposition, and then the secondary, we solve this equation. P1 is just the solution to this one. So pressure, in some sense, fast pressure. And then U is this one, solution to this, or maybe W is much better. Sorry. The W satisfies some boundary condition. This boundary condition guarantees that the W equals 0. I give you later the more precise way, way how to construct W, but anyway, just rough ideas. So we in this way we eliminate that these conditions. So U is given plus U, and P is equal to P1 plus Q. Then we have the equation. Now we have the equation dt gravity. Again, I write then the UF. But now here this important thing is that d equals 0. And still Well, we can reduce this case. But still, pressure P's remain. So final step is the following. Now, again, we consider the Helmholtz decomposition. Now, this means that now we find U, which is solve the boundary into, I think that's H, maybe minus. Sorry, I don't give you some of the why I solve this, just to consider this equation, this weak Neumann-Dirichlet problem. But then now no homogeneous boundary conditions. Then you plug this formula into here, and you have du minus df du plus number of p minus, no, f is now, okay, so f, so now this, now this is also, we write this one. Every f is given in some sense minus. And this is G is a solenoid. Because G satisfies this one. PF is U. Then the equation becomes to minus df du plus number of p minus no q. This is here. Yeah. There's G. Sorry. No. Excuse me. No. Yeah. excuse me. There's F minus W. So F, excuse me, F minus W. Excuse me. So then we write G, here is G, excuse me, G. So this is maybe better to write U. Excuse me. Just this time, just move to left. Then you get to this one first. And then second, if U equals 0 is okay. But now du minus pi is h minus h plus then if you take the inner product with respect to n here, then du ci n is this is vanishes because of this is tangential to the vector n. So you have this one. So here is still vector, therefore right n. So this is scalar n, so minus p to h. And hn is minus u, the definition. So this is you write minus p plus u. So the vector representation is that mu du plus p minus u. Sorry, there is I'm quite sorry, plus because sorry here f is right to g plus w. Okay. Yes, this. Okay, you move to here. So here is a plus graph. See, this is minus. Sorry. This is minus. No. No, plus. Yeah. So here is also plus. Therefore, if we put p plus u is another p tilde pressure, then du plus p is equal to g. U is 0, and mu du minus p tilde I in tilde h tilde is h minus hn And then of course, you gamma. So, okay, so in some sense, summarize the main equation for us is ddu minus d mu du or minus pi equal to f, and then dvu 0, and then mu du pi is equal to h gamma, and sorry, and u gamma d. Okay, of course, initial conditions. I don't care about initial condition so far. Then under assumption that f is solenoidal, and hn, we can reduce the equation to this. Then finally, we can eliminate p. How to do this? Just we take, in some sense, we take the solenoidal decomposition of this part. So meaning is that now let u the solution to, sorry, this is very technical. This du minus du. And then use a function. So d mu d of u minus nabla du. This is the left-hand side. And the boundary condition is this one. So now why I put this, I consider this is just this is Solenoidal. I forgot the name. Lady Mathematician in the Swedish Lady Mathematician. That's come from this. But, in some sense, every fundamental things is come from the, Professor Solenoidal. He's a king of forbidden economics. One kind of kings. One of kings. Solenoidal. Okay, I follow Solenoidal. So I don't know that his idea why he considered this one. But if you consider this one, then you can eliminate the pressure. Meaning that now again we are consider the equation for pressure P. Then now the F is solenoidal. Therefore, for any phi, and then is equal to dtu and number phi minus d du phi plus now u is solenoidal also. Divergence u equals 0. So and then u is solenoidal. Divergence equals 0. So this is 0. So this part is 0. And we are without also give equal 0. Therefore, we write here this one, the plus number 5. Therefore, so this means that number of p minus k, k0. So, this is artificial because of the divergence equal 0. So that you get this. So totally, this is k0u. And then boundary condition. If you look at the nth component of boundary condition, yes, you have boundary condition. Then P is but now here is self-boundary. and this is K. Vanishes. So okay. So therefore, finally we have this. This is a reduced Stokes. This is called the reduced Stokes equation. Here I eliminate the divergence free condition also. Because now today I have no time, therefore I cannot do. But you can say that you can prove that you satisfy the reduced Stokes. Yeah. You can prove dB equals 0. But this is, of course, why I K0, you. No, I don't remember. I don't repeat, but K0 satisfies some kind of weak Neumann-Dirichlet problem, but the point here is right hand side is U, but artificially we write dBu here. And also boundary condition. Yeah, but artificially we put here. And then artificially means that dB equals 0, therefore you neglect these two terms. But if we do not know dB equals 0, and K0U is defined in this way, and the U satisfied this reduced equation, then you can show that dB equals 0. This is a role of K0U. So this is one of the way to eliminate the pressure term. So, okay, so this is the so-called reduced Stokes equations. Then the point is that we don't have any pressure term here. So this is a formulation of the other Stokes equations in the analytic semi-group setting. Because semi-group, if P's appear, then we need the equation also the DTP, but we don't have any DTP. Therefore, only the way to formulate the problem in the semi-group setting, we have to eliminate the pressure P, but this is the way to eliminate the pressure P. So case of U is a functional of U. Okay, sorry, longer time. Thank you very much. Next week I consider, talk about more analytic semi-group approach to the Stokes equation.